we just looked at a very neat way of determining the expression for the coordinates of the point of intersection of two tangents to the parabola, as shown in the box. We did that by looking at the quadratic that was formed by taking the point HK and determining the two tangents that would pass through that. We can use that exact same idea for looking at the equation for the chord of contact. So, as for the circle, we said that given any point HK in the plane, if we draw from that the two tangents as shown to the parabola, then the equation of the straight line that is the chord from those two tangency points represents the equation of the chord of contact. It's sometimes also called the polar line. So, given the parabola, given HK, can we find an expression for the equation of this straight line? Well, let's suppose that the 2 points that are tangents drawn from HK have parametric coordinates AP squared to AP, AQ squared to AQ. Now, we don't particularly want to work them out, but we can write down that's what we're going to call them. Now, from that, from our previous expression for the equation of a chord, we know that the chord through AP squared to AP, AQ squared to AQ, can be written as shown on the next page, the expression here. So that will be the equation of the chord of contact, but we don't want to use P and Q in that. We only know the coordinates H, K, and obviously the parameter A in the parabola. However, we know that that point HK, as shown, has coordinates given by A, PQ, A into P plus Q. We've just shown that. In other words, P plus Q is K over A, P times Q is H over A. That means the equation for this chord, as shown, can have P plus Q and P times Q replaced by these two expressions, which is this, and on rearrangement we have the equation in the box. This is the equation of a straight line. It only involves H and K and the parameter A, and that therefore is the equation of the chord of contact, or the polar line. Now, from that self-same expression, which was the quadratic given by equation 1, which represented a quadratic in T, the 2 points on the parabola from which you can draw two tangents, 2HK, we can clearly see that if this quadratic has a discriminant which is greater than 0, there will be two real roots, and that will be where k squared is bigger than 4h from 1, and that will represent points up here. And we say that obviously all the points that are up here, for which there are two roots for the quadratic, which represents the parameters for the two tangency points on the parabola drawn from HK, this is outside the parabola. And similarly, points here, the other side, we say they are inside the parabola. So everything above here will be y squared bigger than 4ax. Here y squared is less than 4ax, and that's sort of obvious from y squared equal 4ax. If y is sufficiently big for a given value of x, it's above. But we can get that from the quadratic on the previous page, determining whether we've got two roots given by this expression representing the discriminant being positive, two real roots. So finally, in this part, we're going to look at the formula for the points of intersection of two normals. Now this is a little bit harder to work with. So first of all, let's suppose that we take 2 points on the parabola, AP squared 2AP, AQ squared 2AQ, and assume that they intersect at the point x comma y. Now if we write down the expression for the normal through the point here, with AP squared 2AP as its coordinates, and substitute the fact that x comma y lies on that, we get equation 1. That's just the equation for the normal through AP squared 2AP, representing the fact that capital X, capital Y lies on it. And similarly, equation 2 for the other normal also passes through the same point. So our task is to, from these two expressions, to eliminate X or Y to get X and Y in terms of P, Q, and obviously A. So first of all, we can subtract the two equations as given on the previous page, which are here, to eliminate the Y. So if we do that, we get equation 3. Now clearly we want to divide through by P minus Q as we did for the two tangents. In order to do that, we need to replace this difference of two cubes by factorising it as we have here. A formula that we wrote down earlier on. You can soon check that this product gives you P cubed minus Q cubed, or if you've got nothing better to do, you could do the long division. You can clearly see that if P equal Q, this is 0, so P minus Q will be a common factor. So if I replace this difference of two cubes, we should be able to get a simple expression for X by dividing through by P minus Q. So we cancel P minus Q here, P minus Q here, and P minus Q here can be cancelled by just using this difference of two cubes. Again, assuming P and Q are different points, and so P is not equal to Q. So equation 3, having done that division, gives me this, which I can factorise out with the A, and this is the standard form for the x coordinate of the points of intersection of the two normals at the 2 points AP squared 2AP, AQ squared 2AQ. Now we will find later on it's helpful sometimes to put the P squared and the Q squared together by completing the square, but obviously if we complete the square as we have here, we have 2PQ too much, so if we take that off and combine it with this, it gives me minus PQ. So 4 and 5 will be used. Finally, if we substitute for capital X in terms of either of the previous two normal equations, we get capital Y as given by this, and after a little bit of simplification, so some cancellation and some factorisation of PQ, we get the formula for the Y coordinate of the point of intersection of the two normals at those 2 points, and it's minus APQ, P plus Q. So there we have the two forms in the two boxes as shown. Now we're going to go and look at how we determine, for a range of problems, a locus, and there are two typical problems that I'll highlight in the next screencast.